Now let's look at some liquid properties. Check out surface tension, viscosity, capillary action, the meniscus that we see in a burette, vaporization versus condensation, vapor pressure. So let's check out first surface tension. We can see over here in the picture on the right, we can see some sort of a bug kind of walking on the surface of the water. So this is a property of liquids. Results from the tendency to minimize their surface area. To minimize the surface area, liquids form drops that are spherical as long as there is no gravity. Gravity would distort the drop, and it becomes more like tear-shaped if it's falling a distance. You know that surface tension is almost like a skin on the top of a liquid. But in order for that to happen, the liquid has to have probably hydrogen bonding. Well, the surface tension of a liquid is the energy required to increase the surface area a given amount. And you can see that the units here are kind of strange looking units probably to you, but it's millijoules per meter squared. So meter squared is area, and millijoules is a function or a unit of energy. So let's just check out water versus benzene. Water, remember, is very polar. Now look at benzene, very nonpolar, and we get a much lower value. So this means that if a bug was trying to walk across the surface of some benzene, you would have a very difficult time doing that. I like this picture to really kind of demonstrate what's going on with surface tension. So if you look at the molecules in this diagram, the ones within the body of the liquid are kind of spaced a little further apart, and not any particular distance, but further apart than those on the surface of the liquid. And that's because this molecule here, as an example, is being pulled in directions left and right and down, but there's nothing on the top to pull it up. Whereas these molecules here are pulled in all four directions. And that gives us really a little bit higher density on the surface of the liquid, which directly relates to a surface tension. So the stronger these attractions are on the surface of the liquid, the higher the surface tension will be. And that's why we would expect dipole molecules to show a higher surface tension than those that are not dipoles or nonpolar. Now, if you take a look here at, we have 5 molecules, and we're going to check out the viscosity, which is a little bit different than surface tension. So viscosity is the resistance of a liquid to flow. And we've all seen, like, molasses or syrups flowing very slowly. Well, they have a high viscosity. And if we take a look down here, these 5 liquids, they're all nonpolar. You can tell by when you look at the formulas for them, all you see is carbon and hydrogen atoms in the formula. And the molecules get larger as we go down. We can tell that just by looking at the molar masses. Now look at the viscosity. The viscosity goes up as the size of the molecules increases. And was that surprising? The answer is no, because the larger the molecules are, the more attractions they're going to be between one molecule and another. And these are just dispersion forces, so that they're very weak, but they do increase as the size of the molecule increases, because you have more atoms in each molecule to attract each other. Now, if we go back up to the definition of viscosity, we see the unit for viscosity is really called the centipoise, the CP. And a poise is equal to 1 gram per centimeter seconds. So you really kind of, this is really like a density, well, really not a density unit. It's a mass per distance, but it's per second here. And I've used a viscometer before. And a viscometer, it looks like a cup. And then you put the viscometer in it, which is a spindle. It is a metal rod with this, it looks like a little block on the end of it. And the viscometer turns that block, it turns that spindle almost like a mixer within the liquid. And the more force it takes to move that spindle, the greater the viscosity. Factors that affect viscosity: the stronger the molecular attractive forces, the higher the viscosity, liquid's viscosity will be. I just mentioned that earlier. The more spherical the molecular shape, the lower the viscosity. We'll check that out. So molecules roll more easily. And the question here is that you're talking about spherical molecules versus linear molecules. So with a spherical molecule, there's less of the molecule that can get near another molecule. That's why the viscosity is less. And as I mentioned before, two examples. One example could be like this could be honey, or it could be molasses. And I'm going to guess it's honey because we have some biscuits here. And then we have motor oil. Now, motor oil is something that has to maintain a viscosity through a whole range of temperatures. And you know what happens if it's too cold? The oil will turn into jelly. And if it's too hot, the oil will almost resemble water. And so how do we get that viscosity to be pretty much consistent throughout a range of temperatures? Well, raising the temperature reduces the viscosity, as I mentioned. Raising the temperature of the liquid increases the average kinetic energy of the molecules. We know that. The increased molecular motion makes it easier to overcome the intermolecular attractions and the flow. So what you're saying is, if you want to increase the viscosity, heat the liquid. That will work. If you want to increase the viscosity, stir it up. I'll give you a little trick for getting ketchup out of a bottle. You know, a lot of times today you buy ketchup and it's in a plastic bottle. It never used to be in a plastic bottle. It was always in a glass bottle. Glass is much better than plastic. And so the problem with getting it out of a glass bottle is you'd have to, especially if this was a new bottle of ketchup, you'd have to hold it upside down and bang the bottom of it with your hand. And then it might come all flowing out at once and suddenly get ketchup all over the place. Well, if you take a new bottle of ketchup and take the top off it, just take a knife that you have at home, like a butter knife or something, and the knife has to fit into the ketchup bottle. Put it in there and stir it around, and then take it out, and you'll find the ketchup will pour out much more easily because you've decreased really the viscosity. So here we have for motor oil, you see the numbers on the motor oil, like this one says 10W30, this one says 5W40. You know, what do those numbers mean? You know, so we have single weight to multi-weight oils. These are what they call multi-weight oils. A single weight oil will just have one number on it. These are both multi-weights. So these oils contain polymers that curl up at low temperatures and flatten out at high temperatures. So what would polymer curling up at low temperatures do? Well, at low temperatures, we know that the viscosity is going to be higher anyway. And so these molecules, when they curl up, then they actually wind up increasing the viscosity a bit. So that offsets the fact that it's at a low temperature. And then when that oil gets heated up,
we've got two sets of numbers, the 5W and the 30. It might be easy to start with 30. This number relates to how the oil performs at 100 degrees centigrade. And this number relates to how the oil performs when the oil's cool. So let's have a look at this number first, and now we get to this figure of 30. So in order to get this oil heated to 100 degrees centigrade, it's passed through what we call a viscometer or a viscometer. When it enters the viscometer and runs straight through, it's timed, and depending on how quickly it runs through, a reading is given. And that reading relates to its SAE number. Now the slower it travels through here at this temperature, then the higher the number is given, the higher the SAE number. The faster it travels down here, the lower the SAE number. So this all relates to its viscosity or its thickness. The faster it travels through the viscometer, the lower the viscosity, and the slower it travels through the viscometer, the higher the viscosity, so the thicker. The thinner travels through quicker, the thicker travels through slower. And that's where we get these numbers from. So the oil we're talking about has a viscosity of 30, a thickness of 30 at 100 degrees centigrade. So when we're talking about the grade of oils, this is where the last numbers come from. And them numbers are SAE numbers, which have been determined from our viscometer readings. And the reason it's tested at 100 degrees centigrade is because that's considered a working temperature for the average engine. But as most of us know, oils at different temperatures react differently. They have different consistencies, different viscosities. The important thing here is that these figures are for tests at this temperature. So the oil condition relates to this temperature. If we cool the average oil down, there's a tendency to go thicker. The warmer it gets, the thinner it gets, and the cooler it gets, the thicker it gets. So the warmer it gets, the lower the SAE numbers are, and the cooler it gets, the higher the SAE numbers. The trouble with that is that when we come to start an engine, particularly a car engine and a more advanced nowadays, we need the oil to be thinner so that the oil can get into the parts of the engine straight away and do a real good job of lubricating everything. The trouble with getting thicker is the parts of the engine that need lubricating from as soon as you turn the key don't actually get lubricated as much as they need to be. So really then, when the engine is cool, hasn't ran for a while, this number should go up. The temperature will have come down, making the oil thicker. But the clever thing about our oil is its chemical composition makes it so that in cooler conditions, it actually acts like an SAE5. So that oil now, at a cooler temperature, is thin, so that when we first start the key of the car, the oil is nice and thin and lubricates where it needs to from the moment we start the key. And when it gets up to temperature, it acts like an SAE30, so that it's not too thin, because if it gets too thin, at this temperature, again it will lose its lubricant efficiency and put wear on the engine. The way I remember with these numbers is this W here I associate with being winter. So this is the winter condition, the cold condition of the oil. And of course the second number is what it's like at 100 degrees centigrade. So we can see it acts like an SAE5 when it's cool. When it gets up to temperature at 100 degrees centigrade, it acts like an SAE30. And it also relates to these other numbers here. Any numbers that are found on an oil can now, we can work out what they are.
Okay, so much for the video. Let's go back to our PowerPoint presentation. All right, so we saw a little bit about the engine oil. I think it's very fascinating. I hope you're enjoying that. Let's continue on then. Capillary action. The ability of a liquid to flow up a thin tube against the influence of gravity. The narrower the tube, the higher the liquid rises. This is how, for instance, one of the reasons I should say why water is able to go from the ground all the way up through a tree and come out the leaves. Because the tubes that carry this are called, I believe it's called the xylem. The xylem and phloem, I always get them confused. And so that's one of the factors that helps that. So once that's flowing up that tube, then that water, once it gets up to the leaves, it evaporates and that continues to flow. And so a capillary action is something we would see, of course, in the lab. And what we would notice, there actually are things they call capillary tubes, which we'll be seeing in a second. We have capillary tubes that are very, very thin, and I don't know if they still use them anymore in the lab, but we used to use them many times to hold different materials, testing for melting points. So we have two forces going on with capillary action, cohesive and adhesive forces. Cohesive forces hold the liquid molecules together. Adhesive forces attract the outer liquid molecules to the tube surface. So I always think of like adhesive, like an adhesive is a glue that you would put on something. An adhesive might be on, for instance, a Band-Aid, making it stick to your skin. So it's the substance sticking or being attracted to something outside of itself. So that's talking about then the liquid being attracted to the walls of the capillary tube. And here we have some here. And we have, see that the thinness, see how thin this tube is versus the first one. So the wider that, or the larger that diameter, the less the fluid goes up into the tube. That's why even in a glass that you have at home and take a glass of water, you're not going to notice capillary action because the diameter is just way too great. But as you restrict that diameter, then adhesion takes place over, starts to win out over cohesion. And down here we have somebody who is getting ready to give blood, and they are testing the blood for the amount of iron in the hemoglobin. Now, I just gave blood this summer, and they don't do this anymore, which is interesting. They used to have to prick your finger. That's what happened here. They prick that finger, and they just touch the capillary tube to the blood, and it goes up into the tube like that. And then they would bring this tube over to a container that has some copper 2 sulfate in it, solution. It would be a blue solution. And they would just tap the tube then, and the blood would come out, and the blood would sink in the copper 2 sulfate solution. And the further it sank, the denser it was, and then that means the more iron that's present in it. And so if you went to give blood and you found that your blood was floating near the top of that solution, they would say you don't have enough blood in your not enough iron in your blood cells, so we're not going to allow you to give blood today. So the adhetive forces pull the surface liquid up to the side of the tube, and the cohesive forces pull the interior liquid with it. The liquid rises up the tube until the force of gravity counteracts the capillary action. So gravity is keeping it from going up any higher as you see it here. The narrower the tube diameter, the higher the liquid will rise. Now a meniscus is very similar. Here we have a positive meniscus where the liquid is attracted to the sides of the container. And here we have mercury, which gives us an inverted meniscus. The curving of liquid surface in a thin tube is due to the competition between adhesive and cohesive forces. And so when you look here at the meniscus, what's winning out here is it's drawn up the sides of the tube. You say adhesion is greater than cohesion, whereas here cohesion is greater than adhesion. The meniscus of water is concave in a glass tube because the adhesion to the glass is stronger, and mercury is the opposite. Now, why do liquids evaporate? So here we have water as an example. So we have water in a beaker. You see the water molecules are, if the water molecules near the surface have enough kinetic energy, some of them will be able to escape the other water molecules and enter the gas state. And that's really what evaporation is. If these high energy molecules are at the surface, they may have enough energy to overcome the attractive forces. Therefore, the larger the surface area, the faster the rate of evaporation. So if you were to take this same water that's in this beaker and use a larger beaker that has a greater surface area and pour that water into it, you're going to have that water evaporating faster than if it's in the smaller beaker. Now, once that liquid evaporates, it becomes a vapor. And a vapor is not the same as a gas. A vapor is the gaseous state below the boiling point of that substance. So water vapor exists as a gas state of water below 100 degrees centigrade. So vaporization versus condensation. Now, this will only happen if you have a container that is covered, or you're in a part of the world where it's at 100% humidity. So what we have here, if we start on the left in A, we have water molecules in the bottom, so the water is probably just poured into here. And in the beginning, all we have is evaporation. So the water molecules start to fill up in this space. And then after a while, some of these water molecules will, as they're bouncing around, they might hit that surface again and be captured back into the liquid state. And eventually, the two rates of evaporation, which is going up in this direction, and condensation coming back in that direction, will become equal. And that's when you have 100% humidity in here. The vapor pressure is a pressure exerted by a vapor when it's in dynamic equilibrium with its vapor. The weaker the attractive forces among the molecules, the more molecules will be in the vapor state. Therefore, the weaker the attractive forces, the higher the vapor pressure. The higher the vapor pressure, the more volatile the liquid. So here's a graph that shows you diethyl ether, ethyl alcohol, water, and ethylene glycol. Now, diethyl ether used to be used as an anesthetic many, many years ago, and it vaporizes very, very quickly. Ethyl alcohol vaporizes much slower than diethyl ether, but much faster than water. So the problem is you don't have a pure ethyl alcohol around. But what it means is if you put a spoonful of ethyl alcohol, let's say on a board or something that won't absorb the ethyl alcohol, and also put a spoonful of water on that board, and you watch them, well, the ethyl alcohol would evaporate at a faster rate. So it'll have disappeared faster than the water would. And then the last liquid we have is ethylene glycol, and this is an antifreeze, and it looks much thicker. It's a much higher viscosity than water does. So if we take a look at this, you can see for all four liquids, the vapor pressure increases as the temperature increases. And the vapor pressure here is measured in torr. So what happens when the vapor pressure of the liquid equals 760 torr, which is standard pressure? Well, that's when the liquid boils. So you notice the boiling point of water is 100 degrees. We don't even have it for the ethyl alcohol, and then we have I'm sorry, for the ethylene glycol. For the ethyl alcohol, it's less. The diethyl ether is less. So a liquid will boil when the air pressure is equal to the vapor pressure. That's when they boil. So if the air pressure is less, like it is on mountains, so let's say in Denver, Colorado, it's less than it is here, then what will happen is water will boil. In fact, all liquids will boil at a lower temperature. So because the air pressure would be lower. Now it's not going to be dramatically lower, but it will be lower. And here we have water boiling in a tea kettle. When the temperature of the liquid reaches a point where its vapor pressure is the same as the external pressure, vapor bubbles can form anywhere within the liquid, not just on the surface, and this is what we call boiling. So that's how you recognize boiling. Bubbles of vapor are being produced everywhere within the liquid. When you're first heating water, you'll notice that the bubbles of liquid appear on the sides of the container, not within the body of it. That's not boiling. So, call this a roiling boil. So, the phenomenon is what is called boiling, and the temperature which the vapor pressure equals external pressure is the boiling point. So the normal boiling point is the temperature which the vapor pressure of the liquid equals 1 atmosphere. The lower the external pressure, the lower the boiling point. You already had that. Okay. We see at Boston, elevation 20 feet, approximate boiling point of water, 100 degrees centigrade because the air pressure is approximately 1 atmosphere. Go to Denver, Mile High City. Of course, I don't know if it's actually a mile, 5,280 feet equal a mile, but close to, I guess, close enough. So what happens then? The air pressure is lower, boiling point is lower. And would you notice a difference? I don't know. Hard to know. I mean, if you were making a cup of tea or coffee, you're not drinking the water when it's boiling. It's like too hot to drink. So you may not notice it. So what happens as we go up in elevation? Look at the boiling point. It's dramatically different. All right.